All right. So we will move on to chapters 11 and 12, where we are going to first encounter probability. Okay. So chapter 11. Well, it's actually we're not covering the rules of probability yet. We're just this is chapter 11 is on randomness and simulations. And chapter 12 is on sampling. Okay. So these are kind of like a little section, not a whole lot of math involved, just a lot of concepts and ideas. Okay. So we are moving away from the description of data and the description of, I guess, relationships between data, and now we're starting to enter probability, this is about gathering data and just understanding, I guess, a little bit of randomness. Okay. So when we're talking about random events, we're talking about something where the outcome is unpredictable. The outcome is unpredictable, but we can still understand a little bit about the nature of our outcomes. So for example, we can talk about a coin flip. And the coin can land either on heads or tails. And if we're talking about any one coin flip, we cannot predict the outcome of the coin flip. No one can tell me with any kind of with great accuracy whether the next coin flip will land heads or tails. So we cannot predict the outcome, yet we can understand that if I flip the coin many times, overall, I would see about half the time the coin landing heads and about half the time the coin would land tails. Okay, so we can still understand The thing about randomness, though, is that as humans, we are very bad at being random. Okay, arbitrary is not random. So if I were to give you a homework assignment, and I'm not going to do this, but if I said, I want you to take a coin and flip it 100 times and just write down the sequence of heads and tails. Okay. Some of you well, let's say I split the class in half, and I said, half of you, I want you to go home and actually flip a coin and write heads or tails. And then the other half of you, I say, just make up heads and tails, a sequence of heads and tails, as if you were imagining a coin flip in your head. Okay? And so usually, if someone makes up the sequence, heads versus tails, they'll probably say something like this: heads, heads, tails, heads, tails, tails, heads, tails, 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 heads, tails, heads, heads, tails, or something like this. Okay? And at first glance, maybe that seems like, that sounds kind of random, right? But if I were to actually flip a coin, and I'm just going to do a quick simulation here, I will most likely get something very different. I'm going to get, I'm just doing a something like that, okay? There doesn't seem to be a whole lot of difference, but in after many coin flips, we'll see that if it's something truly random, this is possibly truly random, it's not, you'll realize it's not uncommon to see 5 tails in a row or 6 heads in a row or something like that. Even though there's something in our head saying, that doesn't sound quite right, okay? So, is there a reason why? I don't know. Things are random and it's hard to explain. But we can simulate coin flips. We can actually flip a coin. Or if we want to save time, we can simulate coin flips with the assistance of a computer. Okay, and so computers have these what we call random number generators. Okay. And, well, most random number generators will generate a number between 0 and 1. Between 0 and 1, and all numbers, so all up to like 10 decimal places, okay, close to 10 decimals. And every single value in between 0 and 1 have equal probability. Okay. And so we can use this to create simulations of random events. Okay. So, for example, if I wanted to simulate a coin flip, so if I want to simulate a coin flip on the computer, what I would do is I would ask the computer to generate a random number. Okay, so we ask, provide a random number. And it's going to think of a number between 0 and 1. So it might generate something like 0.413377 okay, or something. That only has 8 decimals, but it's good enough, okay? So it generates a random number like this, okay? And so if we want to generate a coin flip, we want to turn these things into coin flips, we can provide a rule, and it will be if the random number is less than 0.5, that means we get heads, and if the random number is greater than 0.5, we will say it's tails. And it will generate, it can provide these random numbers very rapidly, millions of them at a time, and it can assign very quickly whether the coin is, our simulated coin landed heads or tails. Does that sound reasonable? Okay. And that's what we do. And there's a whole field of research within computer science and statistics or engineering on how a computer can generate random numbers. Okay. And there's right, because a computer doesn't actually have its own brain. It just follows a sequence of rules. So how can something that follows a sequence of rules generate something that's actually random? So computers generally, we call these pseudo-random number generators because they're not truly random. So pseudo-random number generator, or RNG. But modern ones are pretty good and nearly indistinguishable from a truly random number generator. Okay? So most today are pretty good. Except for the one in Excel, I think. Well, maybe they fixed it, but for a long time, the random number generator in Excel was known to have serious non-random issues. But maybe it's been fixed. Okay. So we can do stuff like this to simulate a lot more complicated events. Okay. So we could say something like, maybe there is a known, maybe we want to try generating different samples of students, okay? So in this classroom, there's technically 84 of you on the roster, okay? So there's 84 students on the roster. And maybe we want to select a random sample of students. Sample of 10 students. How can we do this? Okay. So I'm going to answer this question in a few different ways. Okay. So one, we'll try using the random number between 0 and 1. Okay. So what we can do is we could list off the students. We got student 1, student 3, student 4, and then their name is Joe, Sam, Bob, etc. We'll make Samantha. So at least we have a girl in there. Okay. And we can say select if the random number generator is between 0.00 and 0.01. Okay. And this will go from 0.01 to 0.02. So between 0.0 and 0.01. And I guess I should say we will bracket off the left and curve the right. So if it actually is, does that make sense? Are you guys familiar with this notation? Where if it actually ends up being 0.01 exactly, it goes to this one, but if it's anything smaller than 0.01, so 0.009999999, then it goes to that, okay? And we can just continue this so on and so forth until we get to the 84th student, which would go from 0.83 to 0.84 bracket, okay? And then we don't have an 85th student. So what do we do with 0.85 to 1.0? Okay, so these we just are discarded. So the computer gives us a whole bunch of random numbers, and we just select our students based on these rules. And if the computer gives us a random number between 0.85 and 1.0, we will just throw it away and ignore it. So that way, each student will have an equal probability of being selected. Yes? Oh, I'm sorry, 0.84 and 1. That's correct. Thank you. Okay, so. Okay, so with this rule setup, every student would have an equal probability of being selected. Does that sound reasonable? Okay. In our book, the book talks about sequences of random numbers, and it's pretty much the same idea, except we are not dealing with a decimal between 0 and 1, where it just gives you a sequence of random digits, okay? And this is what they used back in the day. Back in the day being, I don't know, the 60s or something. And basically the digits 0 through 9, so there's 10 digits, will appear with equal probability. So a sequence of random digits from the book might look like this. Six, five, 1, 3, 3. Okay, and so that it would be, I don't know, some random sequence. Okay, and we could use this to simulate a coin flip. And so to simulate a coin flip, we could say if we get 0 to 4, that is heads, and 5 to 9 would be tails. So our coin flip sequence would be tails, tails, heads, tails, heads, tails, 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 heads, heads, heads. Okay. We could also use this to do the same type of thing that we did over here. If we wanted to draw students, draw a random sample of students. Okay. And basically we would assign every two digits as a random draw. Okay? So look at 2 digits at a time. and we will number the students 01, number students 01, 02, etc., 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 up to, well, we had only 84 students through 84, and then 85, 86, all the way up to 99, and 00 would then be discarded. So according to our sequence, the first student selected would be student 77, then student number 6, then student 35, then student 65, student 13, and then I would need another digit, student 31. Okay. And if for some reason, let's say the sequence went 31, 31 like that, then we would have to ask, is it reasonable to select a student twice? And I would say in this case, no. It would not be reasonable to select a student twice in a sample, so we would not select, we would just have to discard 31. Okay, the second instance of 31. However, when we're talking about a coin flip, is it reasonable to have heads more than once or tails more than once? Sure. So that's why even though I see a 7 once again, I keep that instance of tails. Is that good? Okay, so anyway, that's really all I have to say about randomness. The key thing with randomness is that if we're trying to use random numbers or random digits or whatever it might be, if each of these digits need to show up with equal probability, and whatever it is that you're simulating, the probabilities of those things need to show up equally or with the appropriate probabilities as well. Okay, so if we're talking about selecting students, you have to make sure each student can be selected with equal probability. I think these are simple enough, and I think the questions and the homework in the book are simple enough that you guys will get the hang of it. No problem. Yeah.
So what's the difference between arbitrary and random?
Arbitrary is, I'm just going in my head and I say pick a number, and you say 7 or something. I don't know. If I say pick a number in your head, I might say pick a random number in your head, but you don't have the ability as a human to generate random numbers. We cannot. Our brains are unable to do it. Okay. So if I said, pick a random number between a random digit, 0 through 9, and I ask you to generate a sequence of random digits, and I say make 10 random digits, you won't be able to do it. The numbers that you select may feel like there's no pattern, but they're just arbitrary numbers that you are selecting. And if we were to do some kind of statistical analysis on the numbers you select, we will see that they won't pass these I guess tests. We have tests to see if numbers can be considered truly random. Okay, and it would involve something like taking every 10th digit or every 10th number that's generated and seeing if, looking at that sequence, are all the numbers showing up with approximately equal probability. If I take every 4th number generated, do all the different digits show up with approximately equal probability? Okay, and try as we might, we can't really do it. Okay, you could simulate true randomness by maybe writing the digits 0 through 9 on a slip on pieces of paper, throwing them in a hat, and then drawing a piece of paper out one at a time. That would be something very close to truly random, okay? Or that would actually be truly random. I guess there's a whole philosophical thing of what is random, okay? Are our lives subject to the rules of the universe, and, you know, once the ball has been set in motion, is it going to continue rolling, or are there, you know, random fluctuations? And that answer is I don't think we know the true answer, right? You know, what is free will and fate, and you know, are we fated to, like, are the words I'm saying right now to you something that I'm able to generate out of my own mind and my own conscience on my own free will, or am I just merely the, I guess, subject of some chemical processes happening which just obey the laws of nature and physics?
That's deep.
I don't know, you know? I like to think free will exists, but not everybody even cares, so. Anyway. So we won't get into what randomness truly means at the deep subconscious level. Anyway, chapter 12, sampling. Okay, so we talk about just the idea of randomness, using random digits for simulations. So we might want to gather data, okay? And I think at the beginning of the course we could say there's a few ways for us to get data. One is we can do observational studies, and others we do experiments. I said something like that, right? No? Maybe? Maybe not. I don't know. Okay. Well, anyway, sampling is all about selecting people out of the population, or selecting subjects from a population. Okay? We select subjects from the population. Okay? Because we can't study the population directly, because the population is too large for us to study directly. So ideally, whatever sample we select is representative of the population. Okay? Ideally, we want our sample to be representative of the population. And that way, any conclusions we draw from our sample can then be generalized to the population. And the book uses this analogy, and it's a pretty good one. Let's say you are cooking a giant vat of soup. For a big party, a banquet, hundreds of guests. All right. You want to make sure your soup tastes good. So you want to make sure your soup tastes good. And to do so, do you have to drink all of the soup to make sure every bit of the soup tastes good? No. Okay? That would be ridiculous. You would die. So you are just taking a spoonful, and you're tasting the spoonful, and if the spoonful tastes good, you're going to say, oh, okay, well, the general soup tastes good. All right? But there's a key assumption in that the spoonful that you take is representative of the entire vat. Okay? And so when you taste a thing of soup, what do? Generally, you would stir it up and then take the spoonful, right? And if you're cooking a small pot versus a large pot of soup, okay, does your spoonful need to be larger for the large pot in order for your sample to get a better idea of what the soup tastes like? No. You can use a tablespoon in the small pot, and it'll give you a good idea. You can use the same size tablespoon in the large pot, and it'll also give you a good idea. As long as you kind of do this stirring up business. Okay. So we just need a spoonful to get an idea of what the entire pot is like. Similarly, we just need a sample, and we can get an idea of the population. But let's say as you're cooking, you're like, oh, I need to add a little bit of salt. Okay? So you add some salt to the pot. If immediately after you add the salt, you didn't do any stirring, and you just stuck your spoon in at the top and drank it, you would probably get a very salty thing of soup. Okay? And so, and if you thought that was what your soup tasted like, you would then be very sad because you ruined the soup by adding too much salt. But the key is we would have to stir it, okay? And so we want to get a representative sample. And if our sample is not representative, we would say our sample is biased, okay? So if our sample So when we are taking, selecting random people for a survey, we want to try to avoid getting biased samples. So, let's see. Let's say we wanted to know what people in the United States thought about, I don't know, political stuff. So we ask, do you like President Obama? Okay. Now, if we surveyed the answers to that survey, okay, so there's like the approval rating of the president and all of this, that depends very heavily on the people you ask, okay? If we surveyed people only from Texas, our answer will probably be very different than if we surveyed people from California. Or if we surveyed, if Fox News on their website holds a poll. the results there will probably be very different from if NBC holds a poll on their website. Okay, and that's because the people who visit the website, or the people of Texas, or the people of California, are not necessarily representative of the entire nation. Okay? And so it's, how do we get a truly random sample from the nation? Okay, this is it's a difficult task. But anyway, so let me just talk a little bit more about this. If our sample is not representative, we would say that it's biased. Okay, so to get a representative sample, we want to randomize how we select our people. Okay. Randomness, however, does not guarantee a representative sample. It's our best bet at getting a representative sample, but it doesn't guarantee representativeness. Okay. This would be akin to stirring the soup. And finally, even if the population is huge, you do not necessarily need a larger sample. Okay. It's just the size of the sample itself that matters. Not the ratio between the size, between the sample size and population size. We have a few sampling methods that are worth mentioning. Simple random sampling. This requires a list of everyone in the population. Okay. That list is called the sampling frame. And what we do is we just select people one by one from the sampling frame at random. People or items one by one from the sampling frame at random. And that will give you a simple random sample. Simple enough, okay? The difficult part, so simple random sampling conceptually is simple, or the easiest. The difficult part, however, is getting a list of everyone in the population. trying to get this sampling frame is very hard. So a sampling frame, yes?
5 minutes.
5 minutes. Oh, okay. I better hurry then. So if the, so anyway, I should just write, this is difficult. Alright. You can't use a phone book, okay? So just imagine trying to take a random sample of people in Los Angeles. I don't think there's any listing of every single person in Los Angeles. You could try using a phone book, but then none of you would be listed in it. I don't know. Anybody here listed in a phone book? No, right? Yeah. Yeah, it's really hard, okay? You can look at Pew Research. What they do is they just dial random digits into a phone and hope it rings. And that's what they do. But that's how they get a pretty random sample. And they found that, you know, it's pretty good today because like 98% or 99% of people are connected to some kind of phone. So, okay, we have stratified sampling. All right, I gotta hurry. Stratified sampling, cluster sampling, and systematic sampling. So let me start off with systematic sampling. This is the easiest to explain. If you have a line, just select every nth person. So like select the 10th person, select every 10th or whatever, 10th or 9th, etc. Oh, here's a good example of random versus arbitrary. You go to the airport, they say we've selected you for random sampling, or random screening, but we know it's not random, right? If it was truly random, they could be very transparent with it, and they just say, take this die, roll the die, and if it lands on the X, then you get screened for random sampling. And everybody goes through, they roll the die, if it lands on the X, they get pulled aside for random sampling. Nobody would complain, because everybody would see that it's truly random. But they just say, oh, you got flagged, for whatever reason. And we know it's not random. Okay. Stratified sampling and cluster sampling. They sound similar, but they're different. Stratified sampling, there are subgroups in the population called strata. Generally, the strata are things like gender or race or things like that, okay? And within the population, we know that maybe there's certain proportions of the strata, and we want to make our sample to match those proportions. So in the population, the strata have certain proportions, and we select our sample to match those proportions. Okay. So if you go to an engineering school, maybe it's 90% male, 10% female. For whatever reason, that's still a thing. Maybe it's better now. Maybe it's 80% male, 20% female, or something like that. I don't know why. Okay, you go to MIT, it's like all dudes. Not all dudes, but very heavily dudes. Okay, so when you select a random sample of students from MIT, you want to make sure your sample has the same proportions as the population. So your sample should be 80% male, 20% female. Okay. Cluster sampling. We also have subgroups. But this time the subgroups are called are clusters. And maybe it's difficult to get the sampling frame of individuals. Difficult to get the list of individuals. Relatively easy to get a list of the clusters. Okay. So then you take your list of clusters, select clusters at random, okay. Then do random sampling within the clusters. So for example, if we wanted to get a list, a random sample of all fast food employees, okay? It would be very difficult to get a list of every single person who